Thank you everyone for joining us for today's session. Just a quick sort of intro. Today we have some special guests from Mule, Dragos and Harry, who will be giving us a short presentation towards the second part of the session. But to start off with, we have Clemens, Maia, and Sarah, and myself from Karamba, and we'll be showing you some of the latest updates that we have been working on, let's say, over the last month or so. Feel free to post your questions or comments in the chat or the Q&A, and we will try to adjust them, let's say, during the session or after the session. And we will be recording the session, so we will be posting it afterwards too. So I'm just going to give a quick introduction to what we'll be talking about today. As I mentioned, some of the new features that we will be releasing in the next release, hopefully in the next days or weeks. This legend component, which has been developed by Georg, basically Clemens will show a bit live later, but allows you to actually have this legend dashbar anywhere on your Rhino viewport. Maia will be showing us a bit about the new meshing tools that she's been vigorously working on over the last few months. And there'll be some live demos of how this component works. And once we release this, I think it'll be great for everyone to test it out, because we're really excited to share this with everyone. And the mesh refinement is a special development tool that is great for analysis of shells, especially in Karamba. And lastly, we'll be touching on a PowerBI and Speckle example that I've put together, and showing you how you can, for example, take your Karamba models and send it to Speckle and create these interactive dashboards that show, let's say, the data and results of your model. And as I mentioned, we have Harry and Dragos, who are also going to be presenting from Mule. So, Clemens, would you like to start off with?
Yes, I will share my screen. Just a second. Here we are. So I would like to show you a small little feature, which is, however, quite nice. It's this head-on display legend component, which allows you to fix a legend on your viewport. It's very much like the traditional Grasshopper legend. However, it has a few additional features, like you can scale the legend, you can restrict the viewports to which it applies. So in case I do not specify anything here, it applies to all of them. Then in the context menu, you can change the position, the alignment, justification, and there's one small feature which lets you have this header separately. That's basically it. It's also possible to have multiple components on the viewport. And I would like to thank Rudolf Neumerkel, who gave us the idea about this legend. And Georg, who is not here today, but he is the one who implemented the feature. That's it. So, and I hand over to Maia.
Okay, hello everyone. I'm also going to share my screen. Okay, is that working?
Yes, I see.
Okay, so I'm going to take about 5 minutes of your time and just briefly explain this new measure component that is in development in beta release, almost ready for release. The goal of the measure is to take BREPs in and output a meshing of them. So a quick rundown of the features. The 2 BREPs come in, 2 meshes come out, but they are aware of each other. They will, for example, share an intersection, share edges, share vertices when possible. you can specify a set of points as the input, and these points will show up as vertices in the final mesh. Notice that there's no connection between these points. These are just a cloud of vertices. If you would like to maintain the connections between them, that's where these curve inputs will be useful. And as you see here, surface with curves, the curves can pop out of the surface, but the connection between the vertices are maintained as edges in the final mesh. Not only that, but we also provide your input curves as how they ended up in the mesh, which is here provided as polylines. The paths are maintained. Curve 1, 2 shows up as path 0, path 1. And then, yes, so holes are taken care of. As you can see here, we've got 2 B-reps with 2 holes, a circle, and this is just to demonstrate that the circles are not holes. Holes are what holes are in B-reps. Holes are taken care of. And now we get to the fun part, and this is the new mesh refinement component, which goes into the refine input. And so what this allows us to do is to specify resolution on the mesh, anisotropic resolution. So the way that we're doing this is you can specify curves or points as geometry inputs to this mesh refinement. So we've got here a point and we've got here a curve. And then we've got some parameters that specify how dense the mesh will be within this area of influence. And then the inner and the outer area of this area of influence. And as you can see, there's spheres for points and then tubes for curves that sort of visualize this area of influence, the area being a linear shift from this mesh resolution to this mesh resolution, going from here to here, the outer to the inner radius. And as you can see here, that's what we result in. So this demonstrates two different geometries, a point and a curve, both going into a mesh refinement. This just quickly demonstrates that you can have, by the way, notice that these 2 point and curve are, they're governed by the same mesh settings. If you want different refinement settings, that's no problem. You drag in multiple refinement objects. This one, we've got a point here. So here's our B-rep that we are. Let me focus that. Here's our input B-rep. Here's our output mesh. Here's the two areas of influence. As you can see, I'll select it all. There we go. So we can set different mesh resolutions for this area and this area. That's what I'm trying to say there. As you can see, this one's a bit denser than that one, and the area of influence is a bit different. Okay, then the last option just here briefly is this iteration. And as you can see, one of the big advancements from the previous mesher is anisotropic meshing, where previously we had this, what do you call it? You call it like sort of a geosphere. The latitude, longitude lines will converge and they get a little dense up near the poles. What we have here are, like a nice little distribution around the entire sphere. Same thing with cones. We've got this surface here. And then so just to quickly demonstrate, this is noted by like the iteration. So the 0 iteration is somewhat meaningless, but we found that that's an opportunity to deliver to you the basically what we call the UV space, the mesh as computed in UV space. Before any of this anisotropic handling has been done, it's sort of like the planar graph that's been reprojected into 3D. And then from 1 to n, anywhere greater, this is the same type of calculation. And as you notice, the top of the sphere is a little bit rough there. That's that area near the poles, which needs a little bit more finesse. And as you'll see, 2 is fine. 3, maybe we'll just stick it to 3. 3 is a good spot for that iteration component. And that brings me to the end of the component. So thank you all for your attention.
Thanks, Maya. So now I will share something about the Power BI workflow. This is not really a new development per se, but it's something that we have been testing out a bit on our side with the Speckle export Karamba model to Speckle feature. Speckle themselves have also done a quick fix to structural models, which allows you to now import them into Power BI to create these dashboards. So here I just have a model which has various number of materials and cross sections. Materials and cross sections, so timber, some steel and some aluminium cross sections, and a little bit of cross section optimization involved. So the main aspect is that we're taking a Speckle model, and what we are currently doing is extracting the components of or the elements from the model and adding extra attributes. And these attributes can be, let's say, text, or let's say text string or numbers. So in this case, we've added utilization, normal forces, bending moment, volume, the weight, cross-section element ID, and material. And this has been then sent to Speckle. And with that, I've been able to create a dashboard like this that you can actually interact with the results that we have actually sent using the Speckle model. So, for example, we will be sharing this at a later stage on our website. But for example, if I wanted to now click on all the elements and filter those ones which relate to steel, here you can see them highlighted in this viewer. You can see the sort of sum of weight of all these elements, the average utilization, the average normal force, the average bending moments of these elements. If we wanted to say now look at the columns, for example, you can filter these out. Each of these columns are then sorted in this table here, which has all the results of the calculation that we have sent together with the elements in Speckle. And so you can actually also click on each individual element and see its result and its sort of, let's say, weight distribution as according to its group, or even according to its material, for example, like this as well. So with this, we see that there's a great opportunity for you to actually share like your results or Karamba models with, let's say, others internally or even externally, depending on the Power BI features or licenses that you have available. And I think this unlocks, let's say, a new potential of how Karamba models can be, let's say, distributed or work with as well. So that's it for, let's say, a quick review of this Power BI workflow. And with that, I would like to give the stage to Dragos.
Thanks, Matt. Thanks, everyone. Let me just quickly share my screen. So first of all, thanks for the invitation. Really happy to be part of the event and to join you all today. So I'm Dragos Naicu. Harry is also here on the call, but today I will be presenting a little bit about this project and the whole context in which we use Karamba for it. A brief introduction to Mule Studio to start with, then we'll dive a little bit deep into the project case study. The project is called City Quay Gardens, and it just opened, or is about to open, in Belfast, Northern Ireland. We'll talk about our Karamba experience in developing and engineering this project, and we'll leave with a little note on the course that we do on mastering computational engineering. So a little bit of an introduction to the studio. The Mule Studio was founded by Jack Monroe and Harry Lewis, originally trained as architects and engineer, respectively, but they found a sort of shared love of the computational method and bridging the gap between the disciplines, and also a love of good design in all aspects. So I think that's how the studio came to be. And our computational design team helps people deliver ambitious and efficient projects. We help fabricators, engineers, and architects with bespoke software, structural analysis, complex geometry, fabrication data, and more. And a really key point is that we work at a huge range of scales, from handheld wind turbine repair tools to off-grid cabins to the largest timber structure in Asia. And as we're now going through a process of figuring out how to better talk about ourselves, I'll throw in some new ideas at you to try and summarize how we operate. So we do work in the three-dimensional world, both physical and digital, large and small. So this refers to what we were talking about earlier, from product design like microphones and speakers to the largest timber structures in Asia, and physical and digital, real buildings and web apps. So we span that whole breadth. We believe in striving for innovation and simplicity, i.e., we love a challenge and complexity, but we always aim to reduce it to simple processes, simple designs, simple solutions that ultimately require us to be creative and innovative, so that we bring that complexity down to the right level. We always ask, how could this be better? So we're not afraid to stop and start from scratch and redesign a process or a scheme. And we don't necessarily specialize, as in we all sort of cross-pollinate in between disciplines and learn and grow together. Very briefly, this is the team. So as I said, Jack and Harry, we have our colleague Gianluca and myself. So we cover, amongst us, architecture, design, industrial design, complex geometry, programming, structural engineering, craftsmanship, both physical and digital, and we work together and we combine our skills to suit each project. These are some of the projects. So the ones at the bottom are collaborations with Kraft builders in Canada. So as I said, really, really big scale things. The ones at the top are more pavilion scale. There's a pavilion that was built, I think, in London. This is a flower garden for the Chelsea Flower Show, also in London. And the one on the left, top left, is the one we'll be talking about more today. There's no product images on this page, but you can check those out on our website. So today we'll be really focusing in on this piece of sculpture here. So let's dive into the case study itself. The project is called City Quay Gardens. It's basically a big landscaping master plan for this location in Belfast. It's part of a bigger master plan with office buildings and all sorts of buildings around it. It's also adjacent to a historic Belfast Harbour port office building. I don't remember the exact name, but it's basically this whole area being redeveloped for the public. And our contribution is sort of sneaking up here in the right-hand corner, this structure there. The architect for this is Gillespie's for the whole work. Our scope was limited to these two structures, the nest and the swing. The swing is so as part of this master plan, there's a lot of urban furniture and activity areas and all these kind of things. And the swing is a mixed, it's not a playground swing, but it's a kind of hybrid seating area with a bit of timber design and with these swinging benches attached to it. We also did the same scope for that, but we'll not be talking about it today. And instead we'll focus on the nest. So our scope was full 3D design and detail engineering of these two structures, and the materials were primarily glue laminate steel and a bit of granite for the base of the swing. So this is the nest. On the right, you have a picture from site taken a couple of weeks ago with the whole project completed. And on the left is our model. And it's basically a purely sculptural, iconic sort of gateway to this landscape. It sits above one of the walkways, and it really is meant to signal and attract people into this new public place. Looking at the structure, it is basically a set of 4 inclined steel columns with 10 oak glulam rings suspended on it. And all rings are connected to all 4 columns in this sort of chaotic pattern, hence the name The Nest. It was kind of an allusion to sort of bird's nesty visuals. So we have, that's the primary structure. The rings are connected to the columns by 4 steel connector arms all around, and the whole structure is supported on moment resisting base connections. So you can kind of see here the base plate with some ribs, and the base connections are then fixed into foundations, which in this case were pile caps and pile foundations underneath all 4 legs. What I'm showing here in green is the sort of relative finished soil level for each of the legs. As you can see in this picture, that they sit in the landscaped areas, and some were a bit higher, some were a bit lower, but they had to be, the base connections had to be hidden away from view. In terms of the modeling approach, just very briefly, some dimension constraints were given to us in terms of the minimum free height underneath and the maximum height and the maximum length of the columns, and that generates this green box within which the rings sit. I have to say that the whole model was generated in Grasshopper, really down to the smallest detail. So everything is coordinated with the setting out of the legs and the positions, etc., etc. And everything, obviously, the rings then are parametrically based on that. A little bit of object-oriented modeling was used, using custom speckle objects. You know, each ring became its own little speckle object, and that was very useful for us to transport that information around the script and deconstruct it in multiple places. And if any of you went to Shape to Fabrication a couple of weeks ago, you will have heard Harry and Gianluca talk a little bit more about our approaches for this this thing. It's very useful to be able to package these things around and use them around your script. A little bit of detail on the modeling in preparation for Karamba. So we were very careful about choosing and defining the axes. So these are curved glulam members, meaning the lamellas are circular, and the axes of the members were defined sort of perpendicular to the plane of each ring and into the plane of the ring. And the connector arms were also aligned in that plane so that the axes were also perpendicular and into the plane. And that was something that was, you know, from the beginning, with an eye on member design at the end of the process and checking these members. So we, for the project, we employed a full Karamba3D model. This is some snapshots of the model with the axes and the loading. This was done before the load combination release. So we only had a few, you know, the old way of doing load combinations. the governing ones. But for this particular project, that was not a big problem. It's worth mentioning that it's actually the wind load that is the governing situation here. It's quite a tall structure. It's around 10 meters tall, in a windy location by the port in Belfast. And that was a big driver actually for everything that I'm going to talk about next. But we developed all these things fully in Karamba as part of the modeling process. So, excuse me. As I said, each ring, or maybe I didn't mention it yet, was split into 4 pieces, which meant we had to have splices in between them, which were placed at mid-span in between the columns. And then we also had this to support each ring at those arm locations. And now thinking about the wind load and the lateral stability of the system, the challenge became keeping the glulam member sizes to a minimum because of various project constraints, which then translated into minimizing the connection forces at these locations. 1, timber to timber, i.e. the splice, and 2, timber to steel, i.e. the ring support at this location. And that in turn means fine-tuning the connection rigidities and getting the best possible load path to minimize those forces. That was ultimately what the challenge became. And yeah, so this is where we used Karamba3D. We typically, I like to do this a lot, to have these on-screen results all the time as I'm checking different things. And so you see which load case am I looking at, what's my max deflection. And I think this is a useful thing to have. Whatever you care about, you can quickly display it there. We were using a little bit of a, big scale here in 3D, but in reference to Clemens' earlier point, this is something that's also very useful to always have there, almost as an engineering dashboard. We obviously have the 3D output, and then something that we've been doing a lot recently is customizing the view controls and being able to quickly swap between different types of results. Because in my experience engineering things, sometimes you change a thing and you care about 3 other things, and you really want to quickly see, okay, how did the base reaction change? How did the moment change? What are the stresses now? What if I go back to what I was before? So this kind of thing is very important. So I'll go into the live demo shortly, but just to summarize the outcome, on the left, we see the final design, and we're seeing here a deformed shape with axial forces. So these are the forces in the columns. And on the left is the optimized connection fixity design, let's say, how we design these connections and how we engineered them. Whereas on the right is kind of a non-optimized variant where you can see the problem. It's generating a big portal frame action between the columns and the rings and the columns. And the rings are just obviously the wrong kind of way to transfer moments around that corner. And the sizes were very small. So the left was the final result, which was really helpful. The right would have made the connections basically all steel, very little timber, right, ultimately, or much bigger glulam members. So let's have a look at the grasshopper file. Okay, there we go. So I'll quickly run through some of the options that I'm using here. So first of all, I did mention this on-screen display, which I find super useful. Then I always have a load case selector that allows me to quickly see what I'm looking at. And then here comes a sort of a DIY user interface that I find helpful. So first toggle, you can just show the structure which is just good for a quick snapshot, if you want to take a screenshot and send it to someone. But then you go back to the results mode, and let's go back to wind. So you can either see the deformed structure or the undeformed structure with the same values. Quite useful. Sometimes you want to just see how it moves in that load case, but sometimes then if it's too messy, I just want to see where the values are higher. And the next one is the type of output that we get. So this is deflection. This is utilization. You see I'm using different color schemes just sort of for being visual cleanliness, let's say. Stress output, and then individual moments, shears, and axial. Now in moments already, you see, we got a bit of an issue, and I'll get to that in a minute. Some of other useful things, you can turn this off if you need to take a screenshot, right? You don't need those values. You can put on reactions as well, and then you can tweak that. But going back to the moments, then the visualize ID toggle comes in very handy. So obviously the columns have huge moments, but those are still columns. They're designed for that. They're whatever size they need to be. What if we just look at the rings, right? So here we don't have a legend because we don't have that. We just have the rings. And again, show deformed or undeformed. So it shows them in place. Quite useful to swap between them. And yeah, I think this is very, very, very useful. You can also go specific ring. You can investigate one by one what's happening. And this is where the story about the fixities is relevant. Let's have a look at one of them. Let's choose a good one, maybe this one. So you see, this is the Glula member. This is the connector arm, and it's rotationally free around its own axis. So basically the arc is mounted on a pin on that, and it can rotate, but it is continuous throughout that location. So all 4 locations. But we did put a release into the plane of the ring. So at the splice location, it's like a pinned arch there in the plane of the ring. So it's not carrying moment through there. So this is kind of how it looks with this. Obviously, you can put the numbers on. You can filter out. You can extract the data, put it on the on-screen display here. Would be very useful. But where this was very powerful is in us being able to study the sensitivity of these pins or fixities and see the overall effect. So for example, as I said, there's a full pin there at the end of the arm, and we can see if we sort of reactivate some moment fixities over here, it doesn't do a big, doesn't produce a big difference. Actually, this one does, but the total deflection is still around 90 millimeters. I'll just swap to the other view. I think the calculation is around 2 seconds on this one. That's why there's a small lag. So every time I do a change. So now I'm fully applying, I'm limiting that pin, and now you see what's happening. So if you look in the wind X direction, sorry, I'm getting a little bit into the details of this, but this is wind X. You can see the portal frame action being clearly built. So all these rings are trying to transfer moment into the columns, well, into that arm, and the arm is welded to the column. and the deflection is limited to 73 millimeters, whereas if you actually release it, it increases to around 93, I think, but the moments basically disappear there. So that essentially makes this, tells us how to design this connection and how to keep the member at this size. Maybe it's worth mentioning the members are 91 millimeters wide and 200 deep. So that's really, really small to try and put any moment through that. I think that's all I wanted to show on the live demo. Yeah, I think the different gradients are useful. And yes, one more thing I wanted to show. If I look at the stress input and I look at the rings, you can clearly see the middle axis, which is aligned to the axis of the element. So the ring is bending in its own plane. This is the splice release. There's no moment transferred that way, but there is moment transferred along the ring. And I think, I can't remember which way I did it when prepping. If I fix that rotation now, you'll see a completely different stress distribution, and you see the same thing. It's dumping a lot of moment at that location, and it would be unfeasible to build. So let's go back to this. Yeah, so that's the final design, and really interesting to see. You know, this is the pictures from our model. This is the finished artifact. It's actually just a pin. I think it was an M16 or an M20, single pin through it, which allows that to happen. And the splice is a moment connection in the vertical plane, or sort of vertically to the plane of the ring, but it's the flexibility of the flitch plate in there and the tolerances allow it to sort of kink around, plus it's timber, right? So it's not, it's going to be a little bit flexible. Allows that to work as, you know, we engineered it and we thought about it. And in summary, what we've learned in terms of the effectiveness of Karamba, which might be useful for others to take on board, is developing quick but reliable ways to investigate structural conceptual problems, which means first you have to define your conceptual problem quite well, set up your parametric scheme to take that into account, how you construct your IDs, how you organize your loads, your members, but then you can get reliable results. Secondly, standard ways to interrogate a model and swap between result types. I personally really love doing that, being able to change between stress, deflection, moment, force, base reaction, I think is necessary so that you develop first an intuition of your structural system and how whatever you're working on works structurally, and then also you have the reliable numbers to extract from that. And kind of what I was showing just now is that Grasshopper allows a middle ground between a full-blown UI, you know, with all the buttons to like show results, hide results, blah, 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 and a slower visualization experience, which is if you only have one beam view component, you have to keep going to it and keep changing things, and it's really hard to swap between those. So I forgot to show, but basically this, for the different outputs, I had 6 different beam view components prepared, and I was displaying it. So all these tricks, you know, empower the engineer and leverage this Grasshopper and Karamba3D environment. Yeah, to empower the engineer to make better decisions and quicker and more efficient results as through the design process. So I think this is just scratching the surface, and yeah, great to see all these meetups and the features coming up. A final note, Mule Studio, we've developed a set of courses to give engineers and technicians the understanding and confidence to solve the unique challenges that projects present. The courses are divided in 3 levels, so foundation, advanced, and building and expert. The foundation is really that. It's a strong foundation on Grasshopper and the user interface, data types, data structures, geometry, without which you can't build anything reliable out of it. You can just play, but yeah, so we really value that. Then the advanced is for those looking to deliver projects with some complexity, actually feasible in the real world. And that's when we introduce Karamba3D as well, and FE packages, meshing, advanced data tree management. And the expert is for those who want to be a bit more specialized and goes into more coding, C#, form finding, optimization kind of topics. But yeah, and thank you to Karamba for helping us, teach Karamba as part of the courses. Been doing it for a long time, and it always comes alive after you do the foundation. People understand the basics, and then you're building up to something, and then you put it in Karamba, and you start to see results. It's one of the places where it starts to make sense for the students who join. It's like, oh wow, okay, now I see where all this is going. Yeah, so reach out for a chat whenever. Thank you very much, Clemens and Matt and everyone in Karamba3D team. And thank you all for tuning in.
Thank you, Dragos, for the great presentation. A very impressive project, and I think it's fitting also to see some of the sort of UI and sort of tools that you developed as part of the scripts. And there was already also a question that someone was asking related to this text overlay. And I think now I was just talking internally, and I think definitely we should add that to our list of to-dos because I think it's a great feature. I think a lot of you've probably been using maybe Human or something to do this, and I think it might be good to also add it as a simple feature already native in Karamba because I can imagine I definitely use it a lot, and other people are definitely going to be using it a lot, like the legend component that Clemens showed before too.
Yeah, just one note on that. So if you make it a feature, I think the beauty of it is it's very important to be free to write what you want. So you can be like, my limit is or stay below this, but like be that, but to have that option to write some text on the thing is very,
definitely
very useful.
I think that's so I think that's definitely something that we would look into and add to our list. Is that correct, Clemens?
It was Human, by the way. Yeah, on-screen render I think is a component. Or render text to screen.
Yeah, something like that. Yeah, so I think it's a similar thing to what Georg has developed for the legend component. I think there were a couple of questions related to the presentation. I don't know if you see it here, but I can read them out.
Yeah, go ahead.
One of them was any other FE software used in the project, or was everything analyzed and designed entirely in Karamba3D? I think people were just curious in terms of the full project workflow. I guess you might work.
We did also ship the model to Global RFM, and actually it's good to mention that because it was RFM 5 at the time, and the export component from Karamba, made it basically seamless. So it just sent it to Global, but we didn't do any design there. So design was all done by hand calculations because it's the uniqueness of the Glulam architecture. And also I have to say the results were, the deflections. And whenever I looked between Karamba and Global, it was the same within 0. whatever millimeter. So, but it mainly was the Karamba stuff and the studies of these connection options that drove it, and then it was just the final values that you design for. I think were taken for global, but they were the same. Didn't make a difference.
Yeah, so I think I mean that's a component that is native to Karamba that you can send directly to basically all Beam elements, if I'm correct, Clemens, to RFM, RStub.
Actually,
Currently
I
also
can.
RF.
Yeah, sorry.
Yeah.
Go ahead.
So go ahead.
I was gonna say I remember what happened. It was the load combinations. So I just needed to do more to cover all the wind scenarios, and it was easier to do that in Global actually. But now with the new feature, I think we might have not left Karamba at all, just for a sense check to make sure that it's the same.
Yeah. A second question is more relating to, it's from Raphael. How do you transfer these custom visualization widgets across projects? This UI, I guess, that you were presenting before.
Yeah, so this is not really fully standardized yet. We're building up the knowledge for it, and copy and paste is the simple answer for now, because it's and every project has added a little bit more. So I'm not saying that we found the best way to do it yet. It's just we're incrementally getting better, but we can just take a bunch of this stuff directly copy paste. But it is a question, a more generically good question about how do you transfer these things across projects. Maybe in a couple of meetups time, well, I'll have an answer, a better answer.
I think this is generally something that we also have been thinking about and trying to, let's say, offer more UI features to help work with and interact with Karamba models and results. Of course, if there are any suggestions or recommendations from anyone, please feel free to get in touch with us, share them with us. I mean, similar to like this legend component that Clemens showed, I think a few months ago, Clemens is, we've released a short video about the, let's say, filtering of results according to a plane too. So using the model view. And I'm not sure if people have checked this out, but like it allows you basically to create a section in a way of your models and extract the results in the 2D or a planar view as well. And so if there's requests for additional features that might help you with your setups, I think we would definitely be open up for any of these as well, suggestions.
We have another question from Neil. And the question is, did you undertake any global buckling checks, and were you able to do these with Karamba?
In this case, so global buckling was not necessarily an issue for the columns. It's more of a local buckling, and we did look at the buckling factors. It was not an issue for the rings. We also looked at the frequencies. We did a little side exploration into if it might or might not be susceptible to wind-induced effects, aerodynamic sort of amplifications. Concluded that it would not be the case, but we used Karamba to get the frequencies vibration in various directions. As the wind blows past the ring, would it vibrate up and down due to the vortex, or the columns vibrating left to right due to vortex shedding, that kind of stuff. So yeah, we did use Karamba for those things as well.
Awesome, thank you. Are there any more questions? Maybe from someone?
At the moment, I don't see any, but just some general comments. I think some people are very excited with the meshing tools. So I think Maia, once we release this, I think there'll be a lot of hopefully people testing it out and giving us feedback on the functionality of those tools that you've been developing. So we're super excited to release that very soon.
That'd be great.
I think otherwise, then if there are no other questions, then I would like to thank everyone for joining us today. And once again, a big thank you to Dragos and Harry for their great presentation as well. We hope to have more guests at future presentations too. As I mentioned also in the chat, if anyone has anything they would like to share. Oh, I think my internet is getting bad, but if anyone would have anything they would like to share in future sessions, feel free to get in touch with us, and we'll happily be able to accommodate all these. There is one last question I saw. I don't know if my connection still works.
It does work, your connection.
The question is in the chat, and it's Ahmad asking, how is the joint system simulated if you have overlapping frames on your model?
I'm not sure I follow. We don't have overlapping frames per se. We have each ring is divided into around 80 sub-elements or 80 members, so 20 per quadrant in between each support point, and then they are properly ID'd to be the rings, quadrant start and quadrant end, or the connector has a start and end, and based on that we apply the joints, the releases, or the spring, the stiffnesses. Sorry, I hope that sort of answers the question.
Great, thank you. But otherwise, Matthew? Oh.
Yes, I think that's. I don't know if you still hear me, but I think I would like to thank everyone for joining us once again, and see you all in the next session.
Thank you, everyone.